Hi, everybody. So today we're going to talk about the biodiesel project, specifically the reactions that are happening. So we're going to draw the structures and talk about the synthesis and then some of the calculations that we went over a little bit in class yesterday. We're also going to talk a little bit about macronutrient structures just in relation to biodiesel. So we'll look at lipid structures, structures of fats and fatty acids, because that applies directly to this. The other parts of the macronutrient structures, the carbohydrates and the proteins, we're going to save for another time. I just think that there's just too much to do. And I know a lot of you are still working on mastering some of the stuff from the last couple of weeks that had some difficult things as well. All right, so let's take a look at what we did. Now that we know some things about chemical structures and intermolecular forces and some things about chemistry that we didn't know that first day when we did the synthesis, we can talk a little bit more about what it is that we actually did when we were completing that experiment. All right, so first thing is to just give some general structures of these types of molecules. The oil that we started with was a fat, also known as a triglyceride. Triglycerides are a type of what we call lipids, which are these largely nonpolar molecules in living things. There are other types of lipids as well. They're not all triglycerides, but when we talk about fats, whether it's cooking fats or fats in food, whatever, we're generally talking about specifically triglycerides. And so that's what we used as a starting material. The reason it's called a triglyceride is that it starts with this kind of a structure, which we drew something like this before in one of the practice structures from the worksheet. So you've got 3 carbon atoms and 3 oxygen atoms, and if there were hydrogens on each of these oxygens, we would call that glycerol or glycerin. That's a discrete molecule, and that's going to be one of the products of our synthesis. Since oxygen has to have 2 bonds, we can't just leave them as O's here. So the things that are connected on to these O's of the glycerol are called fatty acids, and they look like this. Each one is connected to a carbon with an oxygen, double bond to it. And then a long carbon chain of anywhere from about 11 to 19 carbons. So something like that. And there's some variation here. So in the oil that we started with, like this isn't an exact description of what that would be. There could be different numbers of carbons. They could have double bonds. In fact, they would. We'll talk about that in a second. But this is the general structure of a triglyceride. That is 3 fatty acids connecting to glycerol to make this one big molecule. And this is what we're talking about when we talk about a fat in general. So that's our starting oil, let's say. Now, just as an aside, we should also discuss the structure of fatty acids. Fatty acids are molecules that look something like what we just drew. If we're thinking about just the discrete molecule, then it's something like this. Now, a fatty acid that looks like this without any double bonds in this chain is known as saturated because it's going to have the most number of hydrogens that it can. So saturated with hydrogens. So if you hear about saturated fats, that's what it's talking about. It's talking about fats made from these types of fatty acids. And then we can also have unsaturated fats where there's a double bond in there. And the geometry of the double bond is such that it kind of changes the structure because double bonds can't rotate the way that single bonds do. So when a double bond is in a chain like this, it kind of makes that chain turn a corner. And if there are additional double bonds, it's going to make it turn around again. And so this would give us an unsaturated fatty acid. This is what we would call mono and unsaturated because there's only one double bond. But if we had multiple double bonds, we'd have a polyunsaturated fatty acid. All right. Now, saturated fatty acids, they're nonpolar, but they're very long and they can pack together very nicely. And so that makes for a relatively strong intermolecular forces. And so saturated fats are generally solids at room temperature. So things like butter, lard, palm fat, shortening, coconut oil, those are primarily saturated fats, which is why they're solids at room temperature. And other things like oils, olive oil, the canola oil that we used in class to make the biodiesel from, those would be largely unsaturated, like this structure here. And that's because those would then have weaker intermolecular forces. All right, so the structure that we made is going to be largely based on unsaturated fatty acids, but the just for ease of drawing, we'll just keep our saturated triglyceride. So what we did in the course of our reaction is we did something called hydrolysis, which means breaking apart with water. Hydro is water, and lysis means to break apart. So there we go, hydrolysis. And if you remember, the reagents we used for that were sodium hydroxide and methanol, CH3OH. And if you remember, we combined those together first. If we said we were just kind of dissolving it, but we weren't actually dissolving, we were doing a reaction. The sodium hydroxide was actually taking away one of the hydrogens from this methanol, and it was making something called sodium methoxide, NaOCH3, which is an ionic compound of sodium ions and this ion here called methoxide, and then the byproduct was water. So making this sodium methoxide, this then reacted with this chain. So really, we call it hydrolysis, but a more correct term is probably methanolysis because we used methanol really more instead of water. And that broke this thing apart. So now the glycerol is on its own. All right, so those oxygens now have hydrogens on them, and that is a complete glycerol molecule. Glycerol. That was a large part of the bottom portion of the waste portion of the initial reaction. So when we drained off that bottom part, you were mostly getting rid of this glycerol, as well as leftover methanol, water, and any extra of this stuff. This is extremely basic, which is why you had a really high pH initially when you drained the waste. So then the other thing that happened was these chains then became free. They were no longer bound to this glycerol. And instead of having that oxygen there, because that went with the glycerol, they were capped with this thing, this methoxide. So hopefully that comes through okay. There's going to be 3 of these. If it's hard to see on the video, remember this is in the class notebook in the content library section, so you can pull this up and look at it and zoom it in or whatever. And there were actually 3 of these. So I'll just say times 3. Each of these 3 chains broke off to make this. And this is what is known as biodiesel. Or you'll see it sometimes shown as FAME, which stands for fatty acid methyl ester. So fatty acid, and then because it's a methyl part on the end, and this type of a functional group is known as an ester, we have a methyl ester. So a methyl ester of a fatty acid. All right, so that's the product. So when we look at the GCMS results, which I should get back tomorrow, we should see some fatty acid methyl esters. And when I post those, I'll give you some instructions on there so you can look those things up and see if that is indeed what formed. And if you see evidence of that most of your sample is made up of fatty acid methyl esters, that's good evidence that you have indeed made the biodiesel that you hope to. All right, so then when we talk about doing the calculations, that's why those calculations on Blackboard are a little bit more, the example calculations are a little bit more complicated than just comparing the beginning mass and the ending mass. Because the beginning mass is a mass of triglyceride, the ending mass is a mass of fatty acid methyl ester. In the meantime, we've added a bunch of methanol and we've gotten rid of a bunch of glycerol, and so the exact masses aren't going to be the same. So we have to think about how many actual molecules of this did we start with, how many of these did we expect to make, and so on. And I'll link a video of some more explanation of myself going through how those things are calculated. All right, so this is the biodiesel reaction. So what should you be able to do here? Well, one, you should be able to draw and recognize these types of structures. But let's look again at a little bit more generally at these hydrolysis reactions and how we can predict them, because they're going to come up again when we talk about proteins and carbohydrates. They're going to come up again later when we talk about polymers. And so we're going to look at the generic reaction of what's going on here. And whenever we talk about generic things in organic molecules, we use this term R, and R just means whatever. It could be carbon, hydrogen, other stuff. It just means some chunk of molecule. So we can say there's some molecule that has this ester functional group, and there can be some other thing attached to the oxygen. We're going to call that R prime. So just here's some chemical stuff, here's some chemical stuff. If we go back up to our biodiesel molecules, for a specific example, in this example, R is the fatty acid that's connected directly to the carbon, and R prime is the glycerol on the other side of the oxygen. But this could apply to any number of esters. So this type of functional group is called an ester. And when water is added, I'll use some colors here to try to make it a little bit clearer. We can think of water as H2O, but we can also think of it as H connected to an OH. And the reason we're going to do that is because as this thing hydrolyzes, reacts with that water, one of those pieces, the OH, goes with the ester and forms what we call a carboxylic acid, a different type of functional group. And then the other part goes with this other chunk. So if you look here, we broke right here. The OR went over here, and the rest of it went here. And then we took the OH from the water and stuck it on there, and we're going to take the H here and stick it on over here to make the alcohol. So if we look at how these functional groups have changed, we took an ester and we broke it into, this is called a carboxylic, that's a Y, acid, and this is called an alcohol. All right, so those are two separate molecules. So we took one molecule, we broke it apart into two separate molecules, and that's hydrolysis. The opposite reaction we're also going to look at later, that's known as condensation or dehydration. But what you should be able to do now is use that template to figure out the products of hydrolysis from any number of other types of structures. So if I drew some random ester, I shouldn't have thought of one so fancy because the drawing thing is giving me some trouble here. So let's take a line structure like that of this ester. And let's say I want to hydrolyze it. So I'm going to react it with water. Now, I should note that water on its own is not really going to do this. You do need a little bit of acid or base to catalyze it, but we'll just say hydrolysis because that could go either way. And we're not really getting into the specifics of the mechanism, like how the actual molecules do this. We just want to know, we start with this thing, how do we break it apart, and what do we form? So if you're watching this right now, pause the video and see if you can come up with the products of this hydrolysis reaction. Then restart it and see if you're correct. All right, well, hopefully you had a chance to try that out. So the first step is, how do we cut this thing? Well, we always cut between the carbon and the oxygen of the ester, not the double bond, the other one. So this is the bond that's breaking here. And then we can just separate those two pieces. So I'm not adding anything else yet. I'm just thinking about how these things are separating. So I got that there, and then on the other side I've got this. Okay, that's not the final answer though, because we have to add water here. We have to add H and OH. And the way that works, just as before, if we use our example here as a template, the OH is going to go onto the carbon double bond oxygen to make a carboxylic acid, and the other H goes to here to make the alcohol. So OH here and H there. And that's it. There's our two products, our carboxylic acid and our alcohol. Oh, can't tell if I'm covering that up or not. Oh, I guess it's just about right. Okay. So that's the products of hydrolysis. So you should be able to do that with, you could do that with lipids, you could do it with, other random molecules now, and that's what we did in our biodiesel synthesis. So if you look at there are two documents in that biodiesel folder that say something about sample calculations or biodiesel calculations, and one of them shows some more of this type of a reaction. I think instead of in line structures, it's done in condensed structures. So you can take a look at that. Then it kind of leads you through the calculations. And then the other one is the one I showed you in class yesterday, which goes through the calculations for the calorimetry. So please work through those calculations either on your own or in your group so that we can see how these fuels compare. And when we come back together in class after spring break, we'll take a look at those numbers and see how everybody's biodiesel looks. So I look forward to seeing that and conferencing with you next week for the midterm evaluation. So please sign up for a time if you haven't already, using the link I posted. If those times don't work for you, I mean, it's during lab, so it should work for you. But if you want to meet online or something, you have some reason that you can't get to campus, then let me know and we can set something else up. We'll be going through all the stuff you've done so far, so make sure you have all the records of the things that you've done working through the material for the first several weeks of this class. What, 8 weeks or so it's been so far. So we will talk about that, and then I will ask you to, based on that stuff and on your level of mastery, to assign yourself a midterm grade. And then we'll revisit that again toward the end of the semester when it's time for final grades. All right, thanks everybody. I will see you next week, but not in lab, or not for a normal lab. Rather, we will be meeting one-on-one for these conferences. So see you then.